Thank you. First, I thank the organizer for the whole conference and giving me the opportunity to present my work. So I will present some kind of high-level talks where it will be a bit of storytelling, right? It's how I understand like the story of ideas in this field from reversible Monte Carlo algorithm to non-reversible algorithm took place in physics. And I acknowledge like all my collaborators along the year, from mathematician to physicist. Okay, so this will be kind of a physics talk. So bear with me if it's a bit hard for the mathematician in the room. Okay, so first I will do like a quick introduction on something statistical physics, just to get the notation agreed between us. And then I will move on to how to upgrade the reversibility dynamics into a non-reversible one. And then if I have time, because otherwise I'm too ambitious for 30-minute talks, I will talk about also scalability in Monte Carlo algorithms. Okay, so first introduction. So the problem of Monte Carlo is that you have high-dimensional integral you want to estimate. And most of the time, when you are n-dimensional, it's impossible to do that analytically. So you will transform this ensemble average into a time average over a discrete sum of samples. And because your computer is only giving you random numbers between 0 and 1, this actually transforms the problem into a problem of mapping random numbers between 0 and 1 into random numbers, like sample, following the distribution P, the target distribution. And since Metropolis work in the 50s, people have been using these random numbers to simulate a Markov chain, to simulate the successive steps of a Markov chain. And if you wait long enough, your Markov chain, if it is correct, will explore your full distribution. This Markov chain is controlled by a master equation, right? So this is a this is a physicist notation, right, to put the little arrow. So the priority to be in A in time t, it depends on your inflow and in your outflow. And your Markov chain will be correct if your target distribution is the stationary distribution of your Markov chain. And so when you build a Markov chain, the goal is to find the right set of transition probabilities that will allow to have this kind of balance that we call global balance. But what happened is that people use detailed balance at the beginning. Also because for physicists it's natural because it is supposed to mimic the natural dynamics of the system. And instead of having this global balance, you'll have a local balance between each pair of states. And the most famous algorithm is the Hastings Metropolis algorithms, where you will accept or not a move based on the difference in energy of the two states. Here, the alpha are just for the what we call in physics a priori probabilities, so the proposal probabilities to propose state J from state I. Okay. The problem with this type of algorithm is that most of the time you need to implement rejection. Is that if you propose a move to a state that is too high in energy, you have to reject the move to have the correct stationary distribution. Okay, and so now people understood that it was kind of slow. Why? Because actually data balance dynamics is most of the time slow, as the natural dynamics of the system is slow. And this can be quantitatively estimated by looking at the correlation between I'm sorry, like there's a big button, but it's to go to the next slide, it's not a laser. So here you look at some test function. So in physics, it could be the susceptibility, the monetization, something, the observable that you guess is the slowest of your system. And you will look at its the correlation. If you're like in some kind of standard Markov chain, it will have an exponential decay. And this will give you this autocorrelation time too. that, in this case of exponential decay, will be linked to the asymptotic variance and the error, the final error in your samples. And so this is fine when you're in easy situation. So for example, here I have a system of Ising spins. So Ising spins like plus or minus, or plus or red, minus or blue, or the inverse. And the type of distribution you have is this type. So M here is a magnetization. So it's just the sum over all the spin. And because here I'm in high temperature, so everything is random. So my magnetization is just a Gaussian around 0, right? But as I cool down the system, as I reduce the temperature, little by little, I will have the operation of big domains, of cluster. And so, until the transition, where I will have a percolation of the cluster. And now my distribution, PM, looks something like this, that is very large. And the problem you have is that in order to explore the full system, you need to be able to move along this large distribution. And what happens is that, so in Ising system like that, we have what we call second order phase transition, and you will have a diffusive behavior if you do like the local algorithm where you take a spin and you flip it plus or minus. Because if you do that, the probability to go from here to there is the probability to flip a whole cluster. And so it's the probability to flip one spin and to diffuse along the cluster. And so it will scale as a length, because it's percolating, it will scale as a length square because of the diffusion. And so until the end, when you cool down and you're back to a solid, some kind of solid phase where you have your two peaks along the negative and positive magnetization. And so we are in the 80s, and people wanted to get free of this curse of what is called the critical slowing down. And this is when cluster algorithms were invented. And the idea is that instead of flipping one spin, why not try to flip a whole cluster and to be able to do this kind of non-local move on the magnetization. And what happened is that you have a reduction of the critical slowing down down to 0, or nearly 0. So how does it work? So here I have my spin configuration, and I will pick one spin, and then I will throw the bonds on the neighbors of same sign. And the bond will have a certain probability. So it's 0 if they are not the same sign, and it has some probability, lower than 1, if they are the same size. And little by little like that, I can construct clusters. And at the end of my cluster construction, I can flip the whole cluster. And so you can have two implementations. You have an implementation where you construct the cluster all across your system, or you just construct one. So here is a pseudocode for just flipping one cluster. And why does it work? It's because you have a direct mapping. So it's a Fortuyn-Castellan mapping. You have a direct mapping between this cluster bound construction and percolation. And at the second order phase transition of the Ising spin, for instance, system, we have this percolation of the cluster. And so that's why you are super efficient, because you will sample like a big cluster and do this non-local move and magnetization. It is efficient, but it is a detail balance algorithm, because the flip is involuntary. So if you apply it twice, you're back to your initial configuration, and you can easily check that the probability to go from one configuration to the others is behaving as a detail balance algorithm. And so this was like a massive success in the 80s, or late 80s. And people tried to emulate that in particle system, which were one of the frontier also in simulation. The problem is that, so I have a particle system here. No, I don't have a flip symmetry anymore. It's because also I'm not on the lattice anymore. I am on some kind of continuum space. And you know, the tricky part is, how do I find some kind of flip emulation in this type of system? And now you'll see how the talk is going to be. The talk is going to be about how do I find a symmetry in the system that allows me to be efficient and to construct translation probabilities. And so the first try was a pivot algorithm from Dress and Kraut. And the pivot algorithm, it's this idea. So it's some kind of flip emulation. It's like you pick a point, random point in your system, and you will do a reflection point of every sphere. So for instance, this white here is transformed into this pink here, this white here is transformed into this pink here, and so on. Then when you have overlap, it will define cluster, and on each cluster, so here you have the blue, the green, and the red one, on each cluster you choose if either you pick the new position or the old one. And then you have a new position. And you have the evolutionary symmetry, like if you apply it back, you're back to this type of configuration. The problem is, this type of algorithm is quite efficient for some system, for some special system. But in the general case, or when you have very high density, what will happen is that you will do a reflection, but then all your spheres will be in the same cluster. And so you'll be just in the pink configuration or the white one, which are actually exactly the same, physically speaking. So it was not enough. So now the solution said, okay, perhaps I should try to move only one sphere by one sphere. And so let's pick a sphere, and I will move it by an increment, a fixed increment. And if it overlaps, I will move the other one, and so on. I will create a chain like that. So it's fine, and actually you can make long chain like that, if you're kind of lucky. But the premise, I don't know if you can see it. So what happens if I have an overlap with two spheres? And the premise is that if you overlap with two spheres, what can you do? If you move one of the spheres, then you're still in an incorrect configuration, right? If you move the two spheres, then what happens if the two spheres overlap with also two spheres, and these four spheres overlap, and so on and so on, and you have what is called the avalanche problem. And actually, what is behind this avalanche problem, as otherwise in Monte Carlo simulation, is because the data balance is broken. And actually, if you just pick the way to get out of this data balance problem is to introduce rejection again. And so you don't have the interest of the cluster algorithm, which were rejection free. And you can see it easily. So for instance, for hardcore system, so hardcore system is like either your configuration is valid, it has a probability 1, either it is not valid, and you have a probability 0. With some kind of normalization, naturally. And so in this type of system, you can see easily that if you want a rejection-free schemes, you need to have symmetric a priori probabilities. So it is not with this kind of plus delta that you will be able to do that, because it is not symmetrical to do plus, 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 plus. And now the question is, okay, so the only thing we have left is to break the delta balance then. And so what we need to do is to break the delta balance in order just to have the necessary condition of a global balance. And if you are greedy, to have like the super necessary condition of maximal balance, is that you have the probability flow, like the minimum probability flows on your state space. So as a physicist, I like to speak like it is hydrodynamics, but it's not the same thing, because we can also link that with incompressibility of flows. It's very beautiful. Okay, and so now we are in this problem, is that in the data balance, we have these nice local symmetries that allow us to develop transition probabilities for any problem. And now we have the problem that, okay, so I'm global balance, I have lost this local symmetry. What can I use to define these transition probabilities in order to have this kind of convective move on my state space? And that's the story of non-reversibility in physics. So it first starts by generalization of lifting. So lifting is the idea that you want to have persistency in your move, but you want to be Markovian, to have a Markov process. And so the way to do that, well, one way to do that at least, is to put pile, sorry, no more battery. Okay, so it could be my harm. It's to extend your state space by a lifting variable. So here it's E. And so for instance, on just this random walk over a loop, you can lift it into a plus and minus replica, the plus where you go in the left direction and the minus where you go on the right. And if you have some kind of potential over that, you just go from one replica to the others to sample correctly your distribution. What happens is that when you have this type of algorithm, you don't have data balance anymore, it's broken, but you have what we call skew data balance. And you can see it like that. So see it like here at the zoom between two sets of configuration. Here, P high is greater than pi j, sorry. So as you propose the move in the plus replica to j, there is some kind of probability that you will reject the move. But here, because we extend the phase space, we'll use this information actually to update the lifting variable. And so in your extended phase space, your scheme is now rejection free. And as you do that, if you reject, then you go back in the minus replica and you go sample in the other direction, which is more likely. And we have this type, we have this kind of data balance here, where you see now that the transition probabilities are balancing each other between the minus and the plus and minus replica. And we can have a rejection-free schemes here by defining the right a priori probabilities. But this is not enough, actually, because in skew data balance, there is data balance. Just like for particles, you have this idea that you propose a move in the I, and then if you go too high in energy, you propose a move, you go in the minus replica where you update in the other direction. So we are in these schemes where you update in the plus replica, and then when you have a rejection, you go in the minus replica. But the problem is that, as you can see by this little cartoon that will act as a proof for now, you have here, let's say we have a mirror symmetry in the potential, like the potential only depends on the distance between the two particles. Then you can use the mirror symmetry. Because moving as you go like that, it's the same thing energetically speaking as to do like that, or reciprocally. And so we use that to get free of the skew data balance. Is that when you have a rejection, instead of going backwards, you will move the other one. So some of you are saying, oh, this is like the Jaster algorithm you just spoke, but you'll see the difference. Now the question is, what if we have more than two particles, which is a problem we have in the Jaster algorithms? So in the Metropolis filter, it's some kind of, everything is tangled up together. So here you have your potential, and every sphere is having its pair interaction with the white one. And the idea here is to use a factorized Metropolis filter in order to extract information. So I just, in my transition probability, it just means that I will extract the product out of the mean. And now, instead of having some kind of bundle of probabilities, I will have a product over independent probabilities. So it means that I can treat every pair interaction in an independent manner. And by doing that, also, it means that if you propose a move, if only one of the factors, so one of the sphere here is rejecting the move, then it means you are rejected. And so you only need to find one that is rejecting the move to know you are rejecting. So this transforms, like any multidimensional problem, into a collection of unidimensional one. And now, how do we solve the avalanche problem? We solve it by a continuous time implementation, in order to be sure that when you propose a move, you will only have, at most, one rejection. And so this is very ugly, I guess, for you, because this is physicist writing. But so in the discrete schemes, the probability to do 1 step, 2 steps, and so on until n steps is a product of successive transition probabilities. And then if you go to the limit with delta equals 0, you find out that you have a Poisson process. And this will be linked, so actually it will be the talk of Joris, to piecewise deterministic Markov processes where you have ballistic trajectories, and at jump times, you will change the direction. And the important point now is that, remember that no rejection and transform into direction change. And so in order to have the good balance, you need to pick the right direction at event. So here, for this kind of problem, it's easy. You just need to move as you go like that. You just... Okay. Okay. As you go, as you move your first white spheres until the first collision, then you move the other one. And the balance is correct because you have the symmetry of the derivative in the energy. You know, the move you propose, if you go like that, this little derivative is the same thing as moving this one. Okay, how much time do I? 10 minutes. 10 minutes, okay. Okay, so now we have upgrade from a local symmetry with reversibility into a non-reversibility algorithm, but that is relying on mirror symmetry. And with also an event-driven implementation because of the continuous time that you need to avoid the avalanche problem. Just to fix a bit the ideas, so the implementation is quite simple when you call this algorithm. Like you pick a sphere and a direction, you will update these spheres along its direction, along the E direction, until you have a first event, and then you will update the other one. The question is now, how do you pick the new direction? So I just show you that, so what was done at the time was to have the same derivative in energy. So it means that when you go, so actually here, when you are going like that, you are going along the gradient, so increasing the energy. And in order to get out of that, to have the correct balance, you need either to do a reflection, or you can do it straight. Well, actually what happens in physics is that straight collision are better, because straight collision are like that, and so you will propagate the move. Whereas if you do a reflection, you will end up going backwards. But this is, this is true for particle system. Okay. And just to get back to the cluster algorithms, that was a bit the goal here. So this is my little pseudocode. And actually, how about I rewrite it in terms of factorize Metropolis filter? So I pick a spin and I flip it. And then I check with any neighbors, according to the factorized probability, if it is accepting or not the move. If it is rejecting the move, then I will update the lifting variable into flipping also this other spin. And so it's kind of nice to understand that you have some kind of continuity between this cluster, this cluster spin move, and just lifting factorized algorithms. So I see lots of highs like that, so you could ask question later. Because I don't have time, sorry. Ah oui, mais j'ai plus le truc là. Okay, I'm sorry. Because now I'm going to show you a little movie. Okay, that's it. Okay, now you have that. This is Okay, so just to show you, now the problem is that now we need the mirror symmetry. And so, okay, so we free ourselves from the detailed balance reversibility symmetry into falling into another one that is quite tight, actually. And the question now is how to upgrade from that. And so let's look at polymers. So polymer is like you pick a sphere and you update it until the other sphere will be too far away and the energy too big. And so just to give you an idea, this will look like that, where you have, so in green you have the Metropolis, and in blue you have some kind of eventual algorithms that will updates the lifting variables on and on depending on the event times. But the problem is that here it's for just x squared, like it just depends on the distance. But what happens if I have angle interaction? So it means m-body interaction, so it's not factorizable. And the problem here is that I cannot just like, if I'm moving the number 2, and I have ejection because at some point the angle is too acute, I cannot move number 1 or 3 because the derivative in energy are not the same anymore. And so what Tobias compound needed, okay, I just have to implement backwards move to go back in the well, but this is not efficient. And the answer is to look at a bigger symmetry, which is a translational invariant you have here. It's because, okay, the derivative, if you move 1 and 3 are not the same, but they add up to moving the 2 backwards. And so the idea, and so you can sample if you move the 1 or the 3, depending on that. And so by doing that, we have updated the need for mirror symmetry into the need for translational invariance. I know you can say, oh, okay, but what if I have a whale and like some kind of trap? In statistics, that is the normal situation. And so I have this whale here, which is some kind of cigar-shaped Gaussian, and I'm kind of forced to do reflection, right, along my potential lines. And the problem behind, the big difference between statistics and physics is that in physics, things are nice. Like the parameters, where the problem is parameterized, is nice, so you can pick a set of eigenvectors in your direction. Here you don't have that, so you need to have the reflection. And the problem is that with the reflection, if you reflect along the isopotential lines, actually it's not ergodic. So you need to introduce back randomness in order to be ergodic. And the solution here is again to upgrade from a local symmetry, because if you look at that, the reflection, it's just from one vector E to give another one in a deterministic manner. But you can have actually a more global handling of the things, because actually the global balance will translate itself by this global balance on the direction change. What does it mean? That at any event, you can pick stochastically another direction. And as it uses the gradient information in a more robust manner, you won't need this type of refreshment in the plane. So I will show you 2 little movies about that. So this will be like just a Gaussian in 2D, where we see the problem of ergodicity. So here you have reflection, why is that refreshment? With refreshment, and here, why you don't have refreshment, but you update stochastically your direction at each event. And so you can see here you're trapped outside a circle of a certain radius, whereas in the others, here you don't need anything. And here's the problem is that you can see that if you put too much refreshment, you can easily switch back to diffusive dynamics. And what happens that if you go now to distributions that are very high dimensional, very cigar-shaped, the problem is that in your small dimension, in small variance dimension, you don't need as much refreshment than in the big one. But the problem is that you cannot pick that. So here you have the Metropolis. Here you have the reflection with refreshment, where we try to be as efficient as possible. And here, when you pick stochastically the direction. And so these little movies are to show you why it is important to try to get rid of any artificial symmetry one creates to actually make its life more easy. Its life would be more easy, but but slower. Okay, how much time do I have left? 2 minutes. Okay, so I will just be really quick. That one other big problem in Monte Carlo, so you have the problem of the physical time of the exploration, but you also have the problem of the computational time. Is that if you have long-range interaction, and for each move you need to compute the interaction with all the other particles in the system, you will have a very slow algorithm, because each time you do a step, it will scale as a number of particles in your system. And if you do a Metropolis, you are forced to do that because everything is bundled up together. But if you look at the factorize, because you only need to know that one factor is rejecting, this can be done in O1. Because this sampling can be decomposed into a sampling of, so with Eugene we call it clock. It's when are you going to reject? Is it as a first factor, second factor, or at the end if you're not going to reject? And you can do this in O1. Yeah, it's also very nice because it's an unstable new process, but. And you can do it in O1 by considering a Boole binary process that would be like constant. And by sampling that, you can directly go to the rejection point, if there is any. The problem is that this is the dark side of the factorize. It's because you factorize, and because you have this product, your acceptance probability will be smaller. And so you need to find the trade-off between increasing the rejection rate and decreasing your complexity. So this is the conclusion. So I hope I have convinced you our determinants is just a way to make one's life easy, and our global symmetry can help with sampling and how to develop non-reversible algorithms and fast algorithms. And also scalability. There are clear frontier, actually. So in physics, it will be the problem of energy extensivity and strong fluctuation that will lead to a factorization that will have like a zero acceleration probability because you have too much term in your product. And also, I end the time to show you that in some system we have a clear reduction of the critical slowing down system, but slowing down phenomena. But in others, we are just getting an offset acceleration. And this is because you have some kind of topological defect in your system that just doing like spin wave, like that for instance, are not able to destroy. In statistics, the problem is more about finding a right trade-off between exploration and ergodicity. And finally, well, this is more the work of Joyce, and the talk of Joyce, like how one can write a quantitative statistical analysis of this type of PDMP algorithms. Okay, thank you for your attention. It's written here, you can see it, but I do it another way.
We have time for one quick question.
There is no link with Hamiltonian dynamics.
Yes.
Actually, you can see it like that. You see the reflection.
Metropolis paper, you can see it as adding just a speed.
No, yeah, exactly. Hamiltonian Monte Carlo, no, I see it just as some kind of lifting algorithm where you extend your phase space with this momentum. And here that will have a Gaussian distribution. But the difference, if you want, between the Hamiltonian Monte Carlo and some kind of reflection non-reversible algorithm is that you'll be discrete time in your Hamiltonian, right? You do this discrete step. And also, if you want, you will accept or reject the move until, I don't know, n leapfrog steps. Whereas here, because of the Poisson process, you're accepting or rejecting the move at each infinitesimal time. I don't know if I'm clear.
No.
Okay, just this one. I'm saying that here, at each step, you're accepting or not the move. Whereas the Hamiltonian is like you do your dynamics, and then you accept or not based on the energy difference, because you did some discretization, so it's not exact.
Okay, so let's end the speaker again.